This lecture I'm going to continue from the previous one. In the previous lecture we discussed about the effect of dielectric on capacitance, and in that case we placed the dielectric material in the entire space in between the two metal plates. Now in this lecture I'm going to explain the capacitance of a parallel plate capacitor partially filled with a dielectric slab. So capacitance of a parallel plate capacitor partially filled with a dielectric slab. Here the word partially is important. You are not keeping the slab in the entire region, but you are keeping it only in a small region, and it is a slab, dielectric slab. So let us consider this case. There is a plate P1, there is another plate P2 like the previous one, and you are placing a slab. So you are placing a slab in between P1 and P2. There is a slab only in small region. You are placing the slab, not in the entire region. And the distance between the two plates is D, like the previous one. Okay, now there will be battery. You will connect it to battery, and then only it will get positive charge and it will get negative charge, but I am leaving that part. I am not connecting it to battery, but please keep it in mind that when you connect to a battery, then only it will get positive and other will get negative. Okay, so connection are there, but I am just leaving those details here. Now when there is no dielectric slab, let the capacitance be C0, and you know what is C0, epsilon 0 A by D, isn't it? Now you are bringing a dielectric slab in between. Let it be having a thickness T, small t. Thickness of the slab will be small letter t. Now apart from the slab, there is some empty space in between the plates, isn't it? In that empty space, you can say that your electric field E1 is equal to sigma by epsilon 0, just like the previous case when two metal plates are there, and if air is in between, field in between the plates will be sigma by epsilon 0. So here, if you consider those regions other than the slab in between the plates, there will be air, and in that region electric field will be sigma by epsilon 0. And due to this electric field, potential in that region V is equal to, V is nothing but electric field into electric field here is E1, and distance when you consider, it is the distance which consists air. Here you can see the total distance is D, out of which T distance is surrounded by your slab. So the effective distance in which air is present is total distance minus the thickness in which slab is placed. That will be D minus T, isn't it? In D minus T region there will be air. In D minus T region there will be air, and in T region there is slab. Total region you will get a D. This is the case. D minus T plus T will be D. So in D region, T region is occupied by slab and D minus T region is occupied by air. So what is the effective length of the region which consists of air? That is only D minus T. So this is a potential in the space without that slab. Okay, in that region where slab is placed, there will be an electric field. Let it be E2. And you know that when you place a dielectric material, electric field will get reduced because there will be an opposite electric field, not equal, there will be an opposite electric field in the dielectric material, and due to this net field will reduce, isn't it, which we discussed in the previous lecture. So net field will get reduced by a factor of K, that also we discussed in the previous lecture. Hence net field in the slab will be sigma by epsilon 0 reduced by K. Original field is sigma by epsilon 0, but in that slab field will get reduced by a factor of K, where K is the dielectric constant of that slab, isn't it? This is what we discussed in the last lecture. So that what will be the field? Let it be V1 in the initial case. Now what will be the field? V2. In this case V2 will be field, that is sigma by K epsilon 0 into distance. How much distance does it have? It is T. Slab is having a thickness of T, and in that region only you are finding the electric field and potential, that will be sigma by K epsilon 0 into T. Now what is the net potential inside? Since there are two materials, air and slab, that's why we found both of them individually or separately, and then we can find the net potential. Net potential V is equal to V1 plus V2, that is E1 into D minus T plus sigma by K epsilon 0 into T. Isn't it? Now V is equal to, we got the equation E1 into D minus T plus sigma by K epsilon 0 into T. Now you know E1. What is E1? Sigma by epsilon 0 into D minus T, where E1 is sigma by epsilon 0. Now sigma T by K epsilon 0. Okay, now you can cross multiply. If you cross multiply, what you will get? Sigma into D minus T into K epsilon 0 plus sigma T epsilon 0 divided by K epsilon 0 square. Now you can see epsilon 0 is common in all the three terms, so you can cancel one epsilon 0, then you will get sigma into D epsilon T K plus sigma into T divided by K into epsilon 0, isn't it? After cancelling one epsilon 0, you will get this term. Now you can take sigma common from the numerator, then what you will get? D minus T into K plus T, isn't it? If you take sigma common, you will get it in the numerator, and denominator will be K into epsilon 0, isn't it? Now we can do one thing. We can take, before that I will write the expression again, sigma into, what you got? Sigma into D minus T into K plus T divided by K epsilon 0. This is what you got. Now let us take K out. If you take K out from the first term, K sigma, if you take, D minus T will remain, but in the second term there is no K, so that you must divide it with a K, because you took a K out, means here you must divide with a K, then only that term will be again same as the previous term, and there is a K epsilon 0 which I am writing here in the denominator. Now you can cancel K from both the terms, then what you will get? Sigma by epsilon 0 into d minus t plus t by k, isn't it? So you got V. Our aim is to find capacitance. Capacitance C is equal to Q by V. Now V you got and Q you know. What is Q? Q is equal to sigma A, because sigma is the surface charge on the capacitor. So if you substitute, what you will get? Sigma into A divided by V. What is V here? Sigma by epsilon 0 d minus t plus t by k, isn't it? So you got the capacitance C, new capacitance. When you place a dielectric slab, you got the new capacitance. Now you can cancel sigma and you can finalize the expression. If you cancel sigma from both the terms, what you will get? Epsilon 0 will move to numerator. Then what you will get? C is equal to epsilon 0 A divided by d minus t plus t by k, isn't it? So this will be the capacitance. Now from this you can again go back to the previous one, that is, if you place the slab in the entire space, that means the previous case, if you place the slab not only in a small region, if you place in the entire space in between the two plates, this is your metal plate, this is the second metal plate P1 and P2, if you place it in the entire space D, then what you will get? We assumed that thickness of the slab is T, isn't it? If you place it in the entire space, what happens? Thickness of the slab will become D, same as the gap, isn't it? So thickness will be equal to D in that case. Then what you will get? This you are having C is equal to epsilon 0 A by d minus t plus t by k. If t is equal to d means d minus t, d and t are same, so this will become 0 and you will get epsilon 0 A divided by t by k will become d by k, because t is equal to d. So you will get k into epsilon 0 A by d, that is k into this is C0. That means you will reach the previous derivation. So previous derivation is a special case of this derivation. When d is equal to t, you will get the previous derivation. Okay, so this is the expression for capacitance when you place a dielectric slab of thickness T in between the capacitor plates. Okay, and from that equation you can go back to the case when that slab covers the entire region in between the plates also. Okay, so anyway, capacitance increases when you place a dielectric in between. That is the conclusion. So all of you please go through these derivations. These are important derivations which can be asked as a 5-mark question.